So as we look at this second unit on probability and statistics, I want to make sure we define some terms here, make sure we understand what we're dealing with and some properties of what we call probability distributions. In this unit as well, we're going to be using your calculators a lot, okay? One thing, we'll be going back and looking at the binomial probabilities that we did back in pre-cal honors, and somebody reviewed that topic. I forget who it was. Okay. But we're going to learn how to do it on our calculators too, which actually makes life super easy. Okay? No, it wasn't, because it wasn't all for nothing. Because actually, the expectation is that you can do it by hand, okay? But there are also applications that lend themselves very easily to using the calculator, and being able to do it on the calculator really makes life a whole lot easier. Okay, so we'll look at the features that your graphing calculator has for doing that. Okay. All right, so let's first of all just remind ourselves what we're talking about with a random variable. Okay, a random variable, we often will use a capital X to represent this random variable, a number form of the possible outcomes of an experiment. A discrete random variable gives us a finite number of possibilities. Remember, a discrete variable has separations between the values, okay? Typically, we're talking about things that are counted, all right? A continuous random variable we'll look at with our normal distribution, our standard normal distribution, okay? Those are things typically that are measured because it's continuous, and we can never quite be 100% precise in our measurements, so it's a continuous distribution, okay? But discrete random variables allow us to have a certain number of possible outcomes, okay? And you can see here where we'll often use this capital X to represent the discrete random variable, okay? Now, let's talk about probability distributions. There are some properties of a probability distribution that you need to make sure that you know, okay? Some of them are, they're basically things that you may have learned before, but just we need to make sure we get them as kind of official properties for these distributions. First of all, notation. The probability that x takes on a value x, notice the difference in notation here. Capital X is our discrete random variable, or any random variable, discrete or continuous. X, this lowercase x, is a specific value of our random variable. Okay? So make sure you understand that. We could write this as probability of x equaling x. Alright, that's notation that you will see here. Alright, here's an example that you're familiar with, tossing two coins. Okay, the variable x, notice that's the random variable, could be 0 heads, 1 head, or 2 heads. Those are individual values of x. So those would be our lowercase x, 1, 2, or 3. Okay? So our random variable could be 0, 1, or 2. The probability distribution, if you guys worked this out, there are 4 possible outcomes, okay? The probability that we don't get any heads is 1 in 4. That's when we get both tails. The probability that we get 1 head, and therefore also 1 tail, would be 1/2. Because either one coin can be the head, or the other coin could be the head. And then the probability that x equals 2, in other words, we get both heads, is 1 in 4. Okay? Now, a couple things here. We have what's called a spike graph. All right, it's kind of like a bar graph, except they're not bars, they're just spikes. Okay, but also we have this column graph. Okay, notice because we're dealing with discrete data, there are gaps between the bars. Remember when we did a histogram, the frequency histograms, when we had continuous data, we had these, side by side touching, okay, because we were talking about ranges. Also remember with those, you would have labeled like 0 on the left side of this bar, and then 1 would have been where these two bars met, okay, for those continuous distributions. This is a discrete distribution, so, this is illustrating a discrete distribution, so there's a gap between them, okay? Now, one of the main things with a probability distribution is the fact that for all of the possible outcomes, x of 1, x of 2, x of 3, up to x of n, whatever those possible outcomes are, the probability of each one added to the others will give us a total of 1, okay? And that's something you guys already know, but seeing the notation here and relating it to these probability distributions is important, okay? You know all the probabilities have to total 1, okay, or 100%. So let's take an illustration. Let's do an illustration of this. First of all, let's read this situation. Pick out what the random variable is representing in this case. Make a probability table. Okay? And then we're going to graph the probability with the spike graph. Since you've probably never done a spike graph before. Not that it's that difficult, but anyways. It says a magazine store recorded the number of magazines purchased by its customers in 1 week. 23% purchased 1 magazine, 38% purchased 2, 21% purchased 3, 13% purchased 4, and 5% purchased 5. Okay? So what is the random variable in this case?
Number of magazines purchased.
What do you guys think about that? The number of magazines purchased.
I think it is the number of magazines purchased.
You agree?
Yeah.
Okay, good.
That's good.
You might look at this initially and think like the percent of magazines purchased or whatever, but what do those percents actually represent?
How many?
The probability. Very good. Okay? The probability that a randomly selected person purchased that many magazines. Okay? So X represents the number of magazines purchased. Okay? So here, if we're creating a table for this, we will put our random variable X in one column. We'll put that the probability that the random variable X equals a specific value of X in the other column. Okay? So you'll notice we have 1, 2, 3, 4, and 5 for our X's. Okay? And then we have our percent. So 0.23, 0.38, 0.21, 0.13, and 0.05. Now I have a question here. Is this a valid probability distribution? And how would I know?
If you add up them to 1, then it's valid. If it's not, then it's not.
Okay, very good. Do these all add up to 1? Okay?
Yeah.
There's
Yes.
61, 82, 95, 100%. Okay? Good. Because you might think, well, I wonder if this takes into account the percent of people who are not buying a magazine. You know, maybe he counted all the people that walked in the door, okay, and he kept track. We don't know based on what they told us, but we would be able to tell, okay, we'd be able to tell or infer from this situation if these percentages didn't total to 100%, then the rest of them must not have bought anything, right? That would probably be a safe assumption to make, okay? So always double check to make sure your probabilities add up to 100%, okay? Now, a spike diagram, we're going to use these percentages, and we have 1, 2, 3, 4, and 5, okay? And you'll notice here all of these are less than 1, okay? So as we're labeling our axes, you know, we know it's not going to go any more than 1, and in fact, what I would probably do is, you know, maybe have it go up by 0.1, okay? So here's 0.1, 2, 3, and 4. We won't need anything higher than that. Okay? So our first spike is going to go up to a 0.23. So approximately right there. Now when you're drawing your spikes, they have a point on the top, and then you just draw a line straight down to your x-axis. Okay, so there's our 0.23. We had 0.38. So just under the 4. Okay. And then 0.21 for 3. So we'll make that just a little lower than the 0.23 was, but still above the 0.2. Okay. 0.4 was a 0.13. So we'll say approximately right there. And then we had the 0.05. So approximately right here. Okay? So that's what our spike diagram would look like for this distribution. Okay? And now you're able to look at a glance. You know, the table is nice, but at a glance, we can now see, okay, we're about 3 times as likely to have a customer purchase 2 magazines as we are to have them have 4. Okay, which if you look at the math, you can see that. 3 times 13 is 39. But just looking at the graph here, you know, you can kind of get that just to visually quickly. You can also see we're almost a little less than double, but almost double the chances that someone buys 2 as someone buys 1 or 3. Okay? And then it's unlikely that someone's going to buy 5. All right? But again, the whole purpose of graphing things is so that we can make inferences, general inferences, quickly at a glance. Okay? Any questions?
That's it.
All right. Good. All right. Now, I've given you a little bit of practice. Again, make sure that you look at your required IP and do that first. There will be additional practice in these documents, in the notes documents, that are not required, okay, but that are there for you if you want some extra practice, okay? So just keep that in mind when you go to do your required IP, go to the required IP document, and that'll tell you exactly which ones you have to do, okay? So, all right, that's it for that.